Okay, we're going to continue on here. We left off last time, which is really one example to go. We were talking about electrolysis. Of course, everybody went home and finished that example. So now we will go over that example together and make sure everybody's on the same page. Then afterwards, we will continue on to the next chapter. So remember, when we're doing electrolysis problems, they do sort of follow a certain pattern. And usually you are given pretty much how long you ran the cell for, at what amperage you ran the cell for. And you're oftentimes asked for how much maybe product you would produce, maybe grams, if it is grams. And as we talked about in the case where we left off here, this is really the electrolysis of water. So in this case, we're looking for really some volumes here of each of the gases, which for water would be obviously the oxygen gas and the hydrogen gas is what you're looking for in this particular problem. A reminder that when you are doing some type of electrolysis problem, and it does mention something about sulfuric acid or some type of acid, again, they will not a lot of times like straight up tell you it's water that you're talking about. They will do something with the acid, and that's sort of how you know it. Remember, electrolysis is really applying electrical current to make a non-spontaneous process occur. So earlier, our anodes and our cathodes as well are really opposite of sort of what happens in a galvanic cell in a spontaneous reaction. For example, we talked about sodium chloride here. And in a normal situation, we're going to be going from sodium metal, for example, to sodium with a +1 charge, which means this guy would be oxidized as it gets reduced, and it would be our anode. While in a normal situation, if we were making sodium chloride, we would go from chlorine to Cl-, which would go from 0 to -1, which would be getting reduced. And again, that would be our cathode. But in a sort of electrolysis process, if we were doing something with sodium chloride, we're actually doing the opposite reactions in each case. We're starting with, for example, sodium with a plus charge and making sort of molten sodium or solid sodium. And we're starting with chloride with a -1 charge and making, say, chlorine. So in this case, we're going from +1 to 0, which means it is actually being reduced and would be our cathode. And this guy's going from -1 to 0, which means it's being oxidized and would be our anode. So remember, sort of our cathode and anode is sort of opposite of when you kind of put it together, when you're kind of breaking it back apart into its elements. So in this case, we're looking for how much oxygen gas and hydrogen gas we would generate at STP. A reminder, STP is the temperature of 273 Kelvin and a pressure of 1 atmosphere. And since we are probably doing some type of gas law here, perhaps PV equals nRT, again, is occasionally what you'll need to use in these type of problems, especially if you're sort of collecting a gas at the end. So we have our half reactions for this, and we're going to really start it here like normal. We're going to take our 7.44 hours, and we're going to convert it into seconds. So 1 hour is like 3,600 seconds. And that's going to give us here 7.44 times 3,600. Easy up on the popping back there. 26,784 seconds there. Our amperage here, which is 1.26 amps, is the same as 1.26 coulombs per second. So that's the same unit. So that's important because we're then going to multiply it by the amperage, which is 1.6 coulombs per second. Our seconds will cancel. That's going to give us 3,374.7.84 coulombs. This is where we use Faraday's constant really to get some moles of electrons, which is ultimately where we kind of want to end up here. So we're going to take, man, that's 96,500 coulombs, right? Per mole of electron. And that will give us 96,500. Or an error. I start at 33747.84 divided by 96,500 gets us 0.3, I will call it 50 moles of electrons. It's at this point that we can now use our balanced half reactions to really get to the elements that we're looking for. So we will do moles of hydrogen or oxygen first. We'll do moles of our oxygen first. So we can see from the half reaction that for every 4 moles of electrons, we get basically 1 mole of oxygen there. So that is what we're going to use. So we'll go with 0.350 moles of electron, using really this kind of stoichiometry from the half reaction. 4 moles of electron gives us 1 mole of O2. And that would get us basically this guy here divided by 4, looks like 0.0875 moles of oxygen. Now, if we do the same thing here for hydrogen, we got 0.35 moles of electrons. From the half reaction here, it is basically, if we multiply the 4 across in that half reaction, we end up with 4H plus 4 electrons gives us 2 H2s. So it's basically 4 electrons to 2 moles of hydrogen. That's also the same as 1 mole of hydrogen is 2 moles of electrons. So obviously you can use either one as it reduces down. So we will have, I'll just use what's there, 4 moles of electrons, 2 moles of hydrogen. Again, you can reduce this down to a 1 to 2, obviously, and it will be the same. And you will end up here with 0.350 times 2 divided by 4 gets you 0.175 moles of hydrogen. Any questions so far? So basically, the time times the amperage it was run for, using Faraday's constant to get us to our moles of electrons, using our moles of electrons and our half reactions, getting us to our elements here. Now what's left is pretty much, in this case, since we are looking for a volume, we will use perhaps a gas law here to solve it. Just like the previous problem we did, if we were interested in grams, we could obviously use the molar mass at this point and get the grams of each of these things that we would have produced. But since we are looking for volume at STP, we will go into that gas law there. And let's just rewrite those. So we had 0.0875, I believe, moles of oxygen, and we had a 0.175, I think, 0.175 of hydrogen. All right, so we could use PV equals nRT. Here we would be solving for volume. Volume would be nRT over P. So if we did this, say, for oxygen, we would put our values in. That would be our moles, which would be 0.0875. Our gas constant for the gas law there, 0.08206 liters atmosphere Kelvin mole, or 0.0821 if you like the rounded number. 273 Kelvin, all divided by our pressure, which would be 1 atmosphere at STP. So again, that is STP conditions, those 2 values there. That gets us 0.0875 times 0.08206 times the 273, going to give us a 1.96 liters of oxygen would be collected here. Again, the moles would cancel, Kelvin will cancel, atmospheres would cancel. Will leave us with moles here. First off, any question on that calculation there? We could do the identical calculation here for hydrogen, which would be nRT over P, obviously just using hydrogen moles, which would be 0.175, 0.08206. 273 Kelvin, and 1 atmosphere here. That gets us 0.175, 0.08206, and a 273 or 392 liters, 3.92 liters of H2. Now, there also is a different way you could have done this, as you might remember from Chem 50, because this is at STP. 1 mole of any gas at STP equals 22.414 liters, which means you don't have to necessarily use the ideal gas law. You could have just took the moles, for example, and went 0.0875 moles of O2. A mole of O2 would be 22.414 liters, and you should end up pretty much with the same number that you got here. And you obviously can do it for this guy as well. So remember, though, if you don't remember this or not sure if you should use this, you can only use it if you're at STP conditions. So if you're not at STP conditions, you should not use that conversion. You should use the ideal gas law. The good news about the ideal gas law is it's frankly can be used at any condition, so it doesn't really matter. So if you're uncertain, always go into the ideal gas law. But because it is at STP, we could kind of shortcut the ideal gas law out if you wanted to. We do see what we saw, I think, in that previous picture, right? We collected about 4 liters of hydrogen to about 2 liters of oxygen, right? So twice as much hydrogen collected as oxygen, which is, again, what we would expect. Question on this electrolysis problem here. Variations of this, as we might have talked about last time, is maybe they do tell you how much you collected as you ran this cell. You got to work your way backwards and maybe figure out what amperage you're running at, how long you ran the cell for, or things like that. So those are sort of the variations on that. Any questions on any of that there? All right, well, that wraps up that chapter, I believe. And that is the last part of what will be on our exam 1 week from today. Good times. There you go. All right, so we're off to chapter 19. So this, I guess, would be final type information here at this point. So we're down to only a couple chapters to go. I think 19 and 20-ish, 21, something like that. So not too bad. So in this chapter, we're going to talk about transition metals, and we're also going to really talk mainly about, towards the end here, complex ions, coordination compounds. But we're going to start out here at the beginning here with a little review of transition metals and some of their properties, as what we will see later on in this chapter. Coordination compounds, complex ions, they basically involve a lot of transition metals in the middle of those. So let's talk a little about some properties and some things about transition metals as you should be familiar with, and some other things that help us understand some of the characteristics of it. One thing that you may be familiar with is effective nuclear charge, which is sometimes referred to as Z effective. And the effective nuclear charge is the charge that the electrons feel as a result of what is sometimes referred to as shielding that's occurring. So for example, let's take our good friend lithium, which has 3 protons, I believe. So basically we have a +3 charge there, and really there's 3 electrons, so 1s2 and like 2s1 type of electron. So the idea behind sort of effective nuclear charge is, and this idea of shielding is, when we think about sort of the electron configuration here, 1s2, 2s1, these 2 lower energy electrons pretty much are close to the nucleus. So they basically feel the sort of full brunt of that +3 charge, and they're going to be held very, very tightly. Now, remember that positive, negative charges, sort of the strength of those things increase with the increasing number of the charge. So that's going to hold those electrons really well. Now, when we talk about this electron here, by the way, which would be what type of electron? That is the valence electron, yes. So that is the valence electron, the outermost electrons, the ones in the highest energy level. By the way, the lower electrons are referred to as core electrons, yes, which are the ones closer to the nucleus. All right, your double jeopardy question is the one involved in bonding is which electrons? It is the valence electrons, right? The ones that are involved in bonding. We'll take a field trip next week back to 15 and see where they are at that. But the idea here is this valence electron that is out here, it really does not feel the full brunt of that nucleus charge because it has these electrons in front of them that's doing sort of a process known as shielding. So it's basically shielding that outer electron from the full brunt of that positive charge. So effectively, it is not really feeling that +3 charge, and you could calculate the Z effective pretty simply. It is the positive charge of like the nucleus minus the number of electrons that are shielding, which means that outer electron is really only feeling sort of a +1 attractive force to the nucleus because of that shielding. And the result of that is that's really why those valence electrons are the ones that are involved in bonding, because they are further away from nucleus. They have some shielding going on. Although they are really sort of still tied to the nucleus, they're not held as tightly as the core electrons. And that's why, again, they're able to either be given away in a ionic compound or they're able to be shared in a covalent compound. So when we look at sort of the periodic table and we go across the periodic table, which is what we're looking at here, sodium, magnesium, aluminum, silicon, and so forth, we do see that the effective nuclear charge does start to increase. So what that means is even the outer electrons are feeling a stronger positive charge than the outer electrons to our guys on the left, which also should make sense, right? Because guys on the left typically will give away electrons. Guys on the right of the periodic table, right, upper right, will basically gain electrons. And that's because even their outer electrons are basically feeling a stronger positive charge. That's also because as you go to the right on the periodic table, you get a bigger numbers. Bigger numbers mean more protons. More protons means the nucleus, right, has a greater positive charge to begin with as well. These are the transition metals, as you hopefully should be aware of where they are at between group number 2 and group number 3 on the periodic table are transition metals. These are sometimes referred to as the first row transition metals. Transition metals start on what orbitals? Where do they come in at? They are the d orbitals, right? And as we'll talk about a little bit here, right? These two guys here are s's. These 6 over here are p's, right? Transition metals, there are d's. Not pictured on the bottom are F block, right? On the periodic table. There's our F block. So transition metals do show very similarities, obviously within a given period and also within a given vertical group. They can have more than one oxidation state, which, as you know, and we've talked about, and obviously the reason why when you name things that have transition metals, you usually use Roman numerals, right, to indicate the positive charges on the metal. So like copper could be +1 or copper could be +2. So when you go to name those guys, you do include copper, say Roman numeral 1 or copper Roman numeral 2 to indicate the charge. There are a few, though, transition metals that do have pretty much fixed charges, and those are zinc, right, and cadmium. They form what type of charge? +2, yeah. Silver is +1, right? So silver is +1 in terms of its charge. Now, the importance of some of these transition metals are, for the most part, they are really involved in complex ion formation, which is sort of what we're going to mainly talk about in this chapter later on. They're really the metal that's in the middle of those guys. And that's a species where we have basically a metal and we have a bunch of what are referred to as ligands attached to it, say something like water. So we've got a bunch of these waters, a bunch of chlorides, things like that, and they make these complex ions. So as we can see here, this is our cobalt, which is our transition metal. These are our ligands. And these ligands are Lewis bases. And what does Lewis bases do? They donate a pair of electrons. Yes. So a Lewis base will actually donate a pair of electrons over to something. That's why NH3 here is a good Lewis base, because if you draw NH3, it is a polar molecule that has those electrons, and it's able to donate it over really to the metal in this case, which is a positive charge. And if something has a positive charge, that means it's electron deficient, right? That's how it gets positive charges. And that's what a Lewis acid is, right? It is something that will accept a pair of electrons. So in this case, it's really the metal kind of working as a Lewis acid, these ligands working as Lewis bases to make these complex ions. And before the chapter is over, you will be able to actually properly name that guy right there, rather than probably what you would normally say, that thing right there, whatever that thing is over there. So you'll be able to just whip out hexamine cobalt 3 ion and go. That's what it's called. Fun times yet to come. I know. Let's not ruin the ending of this chapter yet. All right. Most compounds that do contain transition metals, especially sort of complex ions, they will have some different colors and even the same sort of metal in the middle, and sort of depending on sort of the charge and also the ligands that are attached, will give some different colors to these complex ions. So you could have like a cobalt one that's like blue. You could have one in certain cases that's like a pink sort of solution. Many compounds are paramagnetic. Paramagnetic deals with electrons that are paired or unpaired. They are unpaired electrons. Yeah, so things that have a lot of unpaired electrons are referred to as paramagnetic. So let's talk a little bit about electron configuration. As hopefully you should know, right? You can write electron configuration. Our transition metals do hit up there at the Ds. And this is sort of what's referred to as noble gas configuration. Sometimes when you write electron configuration, that is basically 1s2, 2s2, 2p6, 3s2, 3p6. And that would be really the argon's configuration. And then you would continue on, obviously, 4s2, 3d3 in this case. You hopefully learned how to write electron configuration, and a reminder that there is a really sort of easy way to make a chart that tells you the proper way to do electron configuration. So just in case, on the first energy level, there's S's, right? On the second energy level, there's P's. On the third energy level, that's where D's occur. And on the fourth energy level, right, that is where F's occur. And then you basically just put the numbers underneath, right? 3s, 4s, 5s, 6s, 7s, 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, 6d, and 5f. And basically, this is the way the proper order goes. You just start at the top here and keep zigzagging back and forth. Thing that always screws people up is right about here. It is actually the 4s electrons that get filled first, then the 3d come after those guys. By the way, maximum electrons in an s orbital is 2, right? Maximum electrons in the p subshell is 6, because there's 3 individual p orbitals, right? Maximum in the 5 individual d orbitals, if you took them all together, would be 10. And for the f orbitals or subshells, if you fill them all up, would be 14, right? So this is the order at which you normally would fill these things. And with transition metals, again, they do go into the 4s first, followed by the 3d gets filled. And there is a couple of notable exceptions that you probably learned, and that is chromium and copper. And chromium and copper, there's in the first row transition metals, number 24 and number 29. And the exception is right here at the end. So instead of having basically 2 electrons in the s orbital, it's been found to be more stable experimentally to have 1 extra electron up in the d and 1 less electron in the s. And they're able to do that pretty easily because they're very, very close in energy to begin with. What that does for chromium is basically maximizes parallel spin, which is Hund's rule, and puts an electron in each of the d orbitals. And basically by doing that for copper, it also pairs up everybody for the d orbitals and that. In addition, as you may be aware or not aware, if you pretty much go underneath copper and chromium on the periodic table and kind of in, pretty much everybody in that region, or a lot of those guys in that region, have these type of exceptions where they have an extra electron up in the d orbitals, less electrons in the s. In fact, something like PD there has no electrons in the s. They've all been up to the d orbitals. So there's a lot of exceptions actually below chromium and copper on the periodic table, including silver and stuff like that in their electron configuration. Most people roll with these two as the ones you should know and do come across a lot. By the way, what happens with the energy of these two things here, these two sets of orbitals, once you start putting electrons into the d orbitals? Anybody know what happens? They actually switch in energy. Yeah. So what happens is once you start filling the d orbitals, there's actually a switch in actually the energy, and the 4s orbitals actually end up being higher in energy than the d orbitals. And that's really important for how transition metals lose electrons. Transition metals typically will lose the s electrons first because of that, because there's a switch in energy, and it ends up being that the s electrons are actually higher in energy than the d electrons. Then if necessary, they will dip into those d orbitals. And that is also why sometimes you will see people write electron configuration where all the numbers line up. Like they'll go, 3s2, 3p6, 3d5, 4s2. And that electron configuration is written in terms of energy rather than filling order. Most of the time when chemistry classes that you take, you should always write it based on filling order, which is 4s first, then 3d, but you sometimes see people write it based on energy. So when they do lose electrons, they will always lose the s electrons first, and then if necessary, they will delve into those d's. So if we look at something like Ti here, or even iron, if you take a look at iron, which is number 26 up there. If we wrote the electron configuration for iron, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6 in this case. I believe that should be 26, I think, 10, 26. When we do make, say, something like iron with a +2 charge, that means that iron with a +2 charge has lost 2 electrons. That's what the positive means, right? And the 2 means how many. So the first electrons that it will lose is actually these guys here, because they actually end up being higher in energy. And the proper configuration for iron with a +2 charge would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. Or if you want to shorthand it, this part right here is our argon, 3d6. So you can shorthand it that way. Now, when we go into iron with a +3 charge, it loses 1 more electron. That is 23. So once again, it will lose those 2 electrons that are up here in our 4s, and at this point, once those are gone, it will then come into the d and take out an electron there, and you'll end up with 1s2, 2s2, 2p6, 3s2, 3p6, 3d5 in this case, or argon 3d5. So transition metals are a little different than representative metals. When representative metals lose electrons, they typically end up where on the periodic table? Like potassium, calcium, magnesium. When they lose electrons, they end up, in terms of electron configuration, yeah, they go back to group 8, which is the noble gases, right? That's really the whole purpose of bonding, right? Is for everybody to get to that noble gas configuration. Transition metals really don't get back there, because in order for a lot of them to get back there, that has to lose a ton of electrons to get back to noble gas configuration. So they always will lose the S's. That pattern does follow for the second row transition metals, third row transition metals. They'll always lose the S electrons first, and then they'll delve into the D electrons to do so. Any questions on that there? All right, so we did that. Let's talk a little bit about oxidation states here of our first row transition metals. Again, the common ones here are in reddish, if you can sort of see the red. But it does sort of increase as you kind of go to the middle of the row to our Mn, as you know from our redox experiment, can have a lot of different oxidation states. Most commonly, though, are these guys here, the 2, the 4, and the 7. And for the overall, most common for most of these things in here, probably +2s, +3s are pretty mostly common for that first row transition metals. Let's talk a little bit about ionization energy. Ionization energy is the energy required to remove an electron from the gas state. And when we remove an electron, it will then become positively charged. So a lot of times we associate ionization energy with the formation of a cation. And electrons, as you may know or may not know, they do come off basically one at a time. So they just don't all basically drop off. So for example, if we took something like magnesium, the first thing that would happen is the magnesium would lose one electron. And there would be an ionization energy required to do that. And that would be what is referred to as the first ionization energy, to release that first electron. Next, the magnesium that's lost one electron will then lose a second electron. Also, the ionization energy for this guy would be known as the second ionization energy. And then the magnesium that has lost 2 electrons would perhaps maybe lose another. And that would get us our ionization energy, which would be our third ionization energy, and so forth, as you would continue down there. The general trend in ionization energy on the periodic table is first ionization energy is it increases as you go this way, and it decreases as you go to the left and down on the periodic table. And what we see with first to second to third ionization energy is it gets much harder to remove an electron after you've already done it once or twice or so forth. That is because what happens when we lose an electron? Does the overall size of the ion get larger or smaller? It gets smaller, right? Because it lost some electron cloud. So now even those outer electrons have now moved themselves closer in, and they're going to feel a little bit more of that positive charge from the nucleus and going to be held a little tighter. If you take off the second electron, now everybody's contracted a little bit more. So those outer electrons are even closer to the nucleus and going to be held tighter. So the general trend that we see with ionization energy is as we go from the first ionization energy to the second to the third, it generally increases and gets harder and harder to sort of remove an electron. And if we look at the numbers here, for example, magnesium, which I drew, to remove the first electron, 735, not too bad. To remove the second electron gets like twice as hard or twice the amount of energy to do that. Then we're now talking about, I got to throw in there, like maybe a 7-fold increase there in the amount of energy required to remove that electron. And in the case of magnesium, it does not happen, right? It lays up right about there, right? For magnesium, we really don't see that. That is because when we look at magnesium is 1s2, 2s2, 2p6, and 3s2. Magnesium, which is group number 2, has how many valence electrons? 2, which would be these guys. So once you lose these, you're now into the core electrons, which started out pretty close to the nucleus. And now by the process of losing those 2 electrons or even closer to the nucleus, not going to happen in a normal situation. And that's why magnesium will only go to a +2 charge. Same thing with sodium here. You can see after that first electron, that's a pretty big 10-fold jump in energy if you want to try to pull off one of those core electrons. So it doesn't normally happen. And that's sort of the pattern that you see here. So overall, with ionization energy on the periodic table, first ionization energy increases as you go to the right and up, and decreases as you go down. And between first to second to third, it gets much, much higher and harder to remove an electron. That pattern works really well for what we also know as you go up to the right on the periodic table. We have our nonmetals, which typically will gain electrons rather than lose electrons. And left and down, right, is our metals, which typically are the guys that will lose those electrons. Any questions on that there? Here's a table. It's clear. You should memorize everything on this table. I don't know. But it's just some general trends that we talked about. Obviously, the atomic number, right, which is our number of protons, increases as we go to the right. We just talked about ionization energy. Our common oxidation numbers are +2s as well. Density generally increases as you go to the right on the periodic table. And also size tends to decrease, right, as you go up and to the right on the periodic table. The size of everybody gets smaller, and that's also because of the nucleus, right? There's a lot more positive charge in the nucleus as you go to the right. It's going to bring everybody in closer to each other because of that. Here's our dots for our first, third, and second ionization energy. Another important aspect is what is sometimes referred to as electron affinity. Electron affinity is actually the energy change that occurs when somebody gains an electron. And when we gain electrons, you become an anion. So we oftentimes will associate electron affinity with the formation of an anion. By the way, electron affinity and electronegativity are different things. Electronegativity is the ability of an atom to bring electrons towards itself. They both really have the same trend in terms of the periodic table. Both of them increase as you go this way and decrease as you go down. But electron affinity is really that energy change when somebody gains an electron. Electronegativity is the ability of basically of an atom to kind of bring electrons to itself. It is not a perfect trend, but we do see here in, say, group 7, and it sort of increases as you go up, but then kind of decreases a little bit. So it's not a perfect trend, but electron affinity does generally increase as you go to the right and up on the periodic table, and decrease as you go the opposite way. So all of those sort of trends, again, do sort of come into play with each other in terms of size and electronegativity and electron affinity. As we're moving to the right on the periodic table, we're getting to guys that like to sort of hang on to their electrons a little bit more, as opposed to going to the left and down on the periodic table. They'll get rid of it. This is the reducing abilities here. This is stronger reducing ability, which means if something is a reducing ability, it is going to be a anode in this case, right? So this would be your anode. This would be your cathode. And reducing ability means it's a better reducing agent, I guess is a better way of saying that. Now you may look at those E values, right? And that means that the more positive ones up there on top, which is 2.08, normally the more positive one is which thing? It's your cathode. But in this case, when we look at these reactions, what type of reactions are these? Oxidation or reduction reactions? These are all oxidation reactions, right? Which means if we want the reduction, we would reverse all these reactions, and all these signs would then change to, this was the SRP, minus, 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 plus, which means that does fit with our SRP, right? That guy would be more positive and he would be our cathode. So what we're looking at here is what is sometimes referred to as the standard oxidation potential, the SOP. And this is obviously opposite of the SRP that we've been talking about in this particular case. All right, any questions on any of that there? That is the transition metals. In case you haven't seen them before, there they are. This was a good talk.